Now, in this lecture, we'll find out the radius of a circle using two different methods. In the drawing, we have a circle. We know that the center of this circle is at this point, point O. We also know that line segment AB equals to 6 units in its length. Line segment AD equals to 18 units. Line segment BC equals to 13 units. This angle BAD equals to 90 degrees. This angle ABC equals to 90 degrees also. And our mission is to find out the radius of this circle. So we start with the first method, and we'll do a construction from point C. We'll draw perpendicular on AD. That is to say, this angle equals to 90 degrees, and this angle equals also to 90 degrees according to our construction. We will define the touching point of the perpendicular from point C and AD as E. So we actually created here quadrilateral ABEC. In this quadrilateral we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, plus the fourth angle. In total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore this angle must be also equal to 90 degrees. So quadrilateral ABEC has 4 right angles. Therefore we will write to quadrilateral ABEC as a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, AB equals to EC, but AB equals to 6 units, therefore EC must be also equal to 6 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we'll get that BC equals to AE, but BC equals to 13 units, therefore AE must be also equal to 13 units. And what is the length of line segment ED? Line segment ED, it is equal to AD minus AE. AD equals to 18 units, AE equals to 13 units, and AD minus AE is 18 minus 13, that is 5 units. So ED equals to 5 units. In the next step, we will join points D and C together by a straight line. By joining points D and C, we created here the right green triangle, the right green small triangle EDC. We'll implement the Pythagoras theorem on the right green triangle EDC in order to find out the length of the hypotenuse DC. So in the right triangle EDC, here by PT is the formation for Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the green small triangle EDC is DC, therefore the square of the hypotenuse is DC square, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to EC square plus ED square. In conclusion, according to the Pythagoras theorem, in the right small green triangle EDC, DC square equals to EC square plus ED square. So DC square, that is the square of the hypotenuse, is equal to EC square. EC equals to 6, therefore EC square is equal to 6 square, that is 36, plus ED square. ED equals to 5, therefore ED square equals to 5 square, that is 25. In conclusion, we found out that according to the Pythagoras theorem, DC square equals to 36 plus 25. So DC square equals to 26 plus 36 plus 25 is 61, so this is square equals to 61. We'll take a root out of this equation and we'll get that DC equals to the square root of 61 units. So the hypotenuse DC equals to the square root of 61 units. And DC equals to the square root of 61 units. In the next step, we'll join points B and D together by a straight line. By joining points B and D, we created the right triangle ABD. We will implement the Pythagoras theorem on the right big triangle ABD. Again, pi PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse, the big right triangle ABD is BD, therefore the square of the hypotenuse is BD squared. And it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to AB squared plus AD squared. So according to the Pythagoras theorem in the right triangle ABD, BD squared equals to AB squared plus AD squared. So BD squared, that is the square of the hypotenuse in the right triangle ABD, equals to AB squared. AB equals to 6 units, therefore AB squared equals to 6 squared, that is 36, plus AD squared. Here AD equals to 18 units, therefore AD squared equals to 18 squared, that is 324. So in conclusion, we found out that BD squared, that is the square of the hypotenuse, equals to 36 plus 324. 36 plus 324 is 360. Here we'll substitute 360 by 36 times 10. So BD squared equals to 36 times 10. Here we'll take a root out of this equation and we'll get that BD, it is the hypotenuse of the right triangle ABD, it is equal to the square root of 36 times 10. Here we'll take 36 out of the root. The square root of 36 is 6, so in total we get that BD equals to 6 times square root of 10 units. So the hypotenuse of the right triangle ABD equals to BD, that is actually 6 times square root of 10 units. Here we can write down that BD equals to 6 times square root of 10 units. In the next step, we'll find out the area of triangle BDC. We'll find out the area of the green triangle BDC. So the area of the green triangle BDC, here the squared brackets is the sign for the area. It means the area of triangle BDC will be equal to the base of the triangle times the height to the base over 2. Here I must emphasize that the height to the base must create 90 degrees with the base. So the area of the green triangle BDC equals to the base of the triangle. We will choose the base of the green triangle as BC. times the height over 2. Okay, so in the next step we'll find out the value of the height by extending side BC by a straight line, and then from point D we will draw perpendicular of the extended side BC. So this angle equals to 90 degrees, and this angle it is also equal to 90 degrees according to our construction. By doing this construction we created, but before that we will define the touching point of the perpendicular from point D and the extended BC as F. So by doing this construction we created here quadrilateral ABDF. Inside quadrilateral ABDF we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. That is to say, quadrilateral ABDF that has 4 right angles, it is a rectangle. So I write it down. Quadrilateral ABDF is a rectangle. Why? Because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. That is to say, AB equals to DF. AB equals to DF. But it is given us in the question that AB equals to 6. So we can write that AB equals to 6. And from this equation, 6 equals to AB equals to DF. We will derive that DF, it is also equal to 6 units. DF equals to 6 units. But DF is the height, so the height to the base of the green triangle BDC equals to 6 units. Now we can easily find out the area of the green triangle BDC. So the area of the green triangle BDC, it will be equal to the base of the triangle, the green triangle. The base is BC. BC equals to 13 units, so we substitute BC by 13 times the height to the base. The height to the base that creates 90 degrees with the base, as you can see here. This angle equals to 90 degrees is equal to 6 units. So we substitute the height by 6, all divided by 2. So in conclusion, we found out that the area of the green triangle BDC is equal to 13 times 6 over 2. 6 over 2 is 3, and 3 times 13 is 39. So it is equal to 39 square units. The area of the green triangle BDC, it is equal to 39 square units. Okay? In the next step I will present to you a new rule, and we will implement the new rule in our drawing. This will be actually rule number 2, or rule number 1. According to rule number 1, if triangle ABC, that could be any triangle, is blocked by a circle, so I will draw a circle with triangle ABC that is blocked in it. This is the circle. The center of the circle is at this point, point O. Inside this circle we have triangle ABC that is blocking it. It is blocked by this circle. This is triangle ABC. And here, what is the definition of a triangle that is blocked by a circle? Actually, a triangle is blocked by a circle only and only if all of its three vertices are touching the circle. Exactly like in this drawing, you can see here that this vertex of triangle ABC touches the circle, touching the circle at point A. This vertex of the triangle is touching the circle at this point, point B, and this vertex is touching the circle at point C. So only if all the three vertices of the triangle are touching the circle at different points, only then we can say that the triangle is blocked by a circle. And we define the radius of this circle as capital R. Here OM equals to capital R according to our definition. So whenever you have a triangle ABC, that could be any triangle, that is blocked by a circle, then the radius of this circle, that is to say capital R, will be equal, here the length of side AB equals to A units in its length, side BC equals to B units in its length, and side AC equals to C units in its length. So the radius of this circle, capital R, that blocks the triangle will be equal to the side lengths of the multiplication of the side lengths of the triangle by each other, that is to say A times B times C, over 4 times the area of this triangle ABC. Okay? So we actually can implement the new rule number 1 in our drawing. Why? Because in our drawing we have the green triangle BDC, and this green triangle BDC is indeed blocked by this circle. Why? Because this vertex is touching the circle at point B, this vertex is touching the circle at point C, and finally this vertex of the green triangle BDC is touching the circle at point D. Therefore, it is definitely, the green triangle BDC is definitely blocked by this circle. Therefore, we can implement here rule number 1. So I write it down. The green triangle BDC is blocked by the circle. Therefore, we can implement here rule number 1, and according to rule number 1, we will define the radius of this circle as capital R, here OM, that is the radius of this circle, it is equal to capital R according to our definition. So the radius of this circle, that is to say capital R, will be equal to the multiplication of the side lengths of the triangle by each other, that is to say BD times DC times BC over 4 times the area of the green triangle BDC. Repeat again. Because of the fact that this green triangle BDC is blocked by a circle, we can find out the radius. We can implement here rule number 1. That is to say, we can find out the radius of this circle, that is equal to capital R according to our definition. according to rule number 1. And according to rule number 1, the radius of the green circle and the radius of the circle that blocks the green triangle BDC will be equal to the multiplication of the side lengths of the triangles by each other. That is to say BDC times DC times BC over 4 times the area of this triangle BDC. So capital R, that is the radius of the circle that blocks triangle BDC, will be equal to BD equals to 6 times square root of 10 units times DC equals to the square root of 61 units times BC equals to 13 units over 4 times the area of the green triangle BDC. And we already found out that the area of the green triangle BDC equals to 39 square units. So actually that is actually the answer to the question, because we asked to find out the radius of this circle that blocks the green triangle, and we found out that the radius of this circle, that is to say capital R, is equal to this expression. Now we just have to simplify this expression, and we finished with the first method. Okay, so here we will divide both the numerator and the denominator of this expression by 13, and we get that the radius of the circle that blocks the green triangle BDC equals to 6 times square root of 10 times square root of 61. 13 over 13 is 1, so 13 will get cancelled. So in the numerator we left only with 6 times square root of 10 over square root of 61 over 4 times 39. 39 over 13 is 3. So in the numerator, in the denominator we left only with 4 times 3. So the radius of the circle that blocks the green triangle BDC, it is equal to 6 times square root of 10 times square root of 61 over 4 times 3 is 12. Here we will divide both the numerator and the denominator of this expression by 6, and we get that the radius of the circle equals to 6 over 6 is 1, so 6 will get cancelled, and we left only with square root of 10 times square root of 61 in the numerator over 12 over 6 is 2. Okay. Here we will use the algebraic identity that states that the square root of A times square root of B equals to the square root of A times B. So the radius of the circle equals to the square root of 10 times the square root of 61 according to this algebraic identity will be equal to the square root of 10 times square root of the square root of 10 times 61 over 2. That is to say the radius of this circle, the radius that we are looking for, that is to say capital R, will be equal to the square root of 10 times 61 is 610 over 2. So the radius of this circle, that is to say capital R, equals to either the square root of 610 over 2 units, or in terms of numbers it is equal to 12.349 units. So finished with the first method. In the next step I will present to you how to find out the radius of this circle according to the second method. So in the second method, in the first place, we will do all the things that we have already done in the first method. That is to say, from point C we will draw perpendicular on AD. So this angle equals to 90 degrees. In this angle it is also equal to 90 degrees according to our construction. We will define the touching point of the perpendicular from point C and AD as E. So in the quadrilateral ABC we have 1, 2, 3 right angles. Therefore the fourth angle must be also equal to 90 degrees. I will not repeat on the reason. We've already done it in the first method. So inside quadrilateral ABC we have 4 right angles, and therefore quadrilateral ABC is a rectangle. But we know that the opposite sides of a rectangle are equal to each other. That is to say, AB equals to EC, but AB equals to 6, therefore EC will be also equal to 6. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we will get that BC equals to AE, but BC equals to 13, therefore AE will be also equal to 13 units. And what is the length of ED? ED equals to AD minus AE. That is 18 minus 13, that is 5. So until now we have already did all the things that we did here in the first method. From now on we will continue with the second method. That is to say, from point O we will draw perpendicular on chord BC. So actually this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from the center of the circle, that is to say from point O and chord BC as capital N. We will define the touching point of the perpendicular from point O to AD as M. In the next step I will present to you a new rule, and we will implement the new rule in our drawing. According to the new rule, that will be actually rule number 2. We have a circle that could be any circle. The center of this circle is at this point that we will define as point O. And we have here chord BC. This chord BC could be any chord. And from the center of this circle, that is to say from point O, we will draw perpendicular on chord BC. So this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and BC as M. So according to this rule, rule number 2, a perpendicular from the center of a circle to any chord bisects the chord. You write it down. A perpendicular from the center of a circle to a chord bisect the chord. So here, from the center of this circle, that is to say from point O, we have perpendicular OM to chord BC, and according to this rule number 2, this perpendicular OM bisects chord BC. That is to say, BM equals to MC. Okay, BM equals to MC. So, whenever you have a perpendicular from the center of any circle to any chord, it will bisect the chord. Okay? So, perpendicular from a circle to a chord, or you can write also to any chord. To any chord, bisect the chord. Here, chord BC could be any chord. So actually, we can implement rule number 2 in our drawing. Why? Because in our drawing, we have the perpendicular ON from the center of this circle, that is to say from point O towards chord BC, and according to rule number 2, the perpendicular ON bisects chord BC. That is to say, BN equals to NC. So I'll write it down. In our original drawing, we have perpendicular ON this from the center of the circle, that is to say from point O So in our original drawing, we have the perpendicular ON from the center of the circle, that is to say from point O to chord BC. And according to rule number 2, it will bisect the chord BC. That is to say, BN equals to NC. It bisects the chord according to rule number 2. That is to say, BN equals to NC. According to rule number 2. Okay. So BN equals to NC. In the next step, we will focus on quadrilateral ABMN. In this quadrilateral, we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. Therefore, quadrilateral ABMN is a rectangle, and we know that the opposite sides of a rectangle are equal to each other, that is to say AM equals to BN. I'll repeat again. Quadrilateral ABMN is a rectangle because it has 4 right angles. And according to the rule that the opposite sides of a rectangle are equal to each other, we will get that AM equals to BN. Likewise, in the next step, we will focus on the lower quadrilateral MNEC, this quadrilateral. In quadrilateral MNEC, we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. And therefore quadrilateral MNEC is a rectangle. Repeat again, the lower quadrilateral MNEC is a rectangle because it has 4 right angles, and we know that the opposite sides of a rectangle are equal to each other. That is to say, MN equals ME, this ME equals to NC. So we can summarize what we did until now. According to rule number 2, we found out that Bn equals to Nc. And according to the rule that the opposite sides of a rectangle are equal to each other, we found out that Bn equals to Am. So we can write here that Bn equals to Am. And we also found out that Nc equals to Me according to the rule that the opposite sides of a rectangle are equal to each other. So we can write here that Nc equals to Me. And from this long equation, Am equals to Bn equals to Nc equals to Me, we will derive that Am equals to Me. Am equals to Me. Repeat again, side Am equals to side Me. Okay? In the next step, we will extend line segment DA, this line segment DA, until it touches the circle, and we'll define the touching point of the extended line segment DA and the circle as point F. So by doing this construction, we created here chord FD. This is chord FD. And a couple of minutes ago, we drew perpendicular ON to chord BC. So ON is a perpendicular, it is absolutely a straight line. ON is a straight line because it is a perpendicular. So if we focus on the upper side of the straight line ON at point M here, the sum of the angles on one side of the straight line is equal to 180 degrees. So the sum of the angles on the upper side of the straight line ON at point M must be equal to 180 degrees according to the rule that I mentioned. That is rule number 1. So which angles we have at the upper side of ON at point M? We have this angle that is equal to 90 degrees plus the missing angle. In total they must be equal to 180 degrees according to rule number 1. So the missing angle, here this angle, must be equal to 90 degrees. In order to complete the sum of the angles on the upper side of ON at point M to 180 degrees, the missing angle must be equal to 90 degrees. Likewise, if you focus on the lower side of the straight line ON at point M, here also the sum of the angles must be equal to 180 degrees according to the sum rule, rule number 1. So which angles we have at the lower side of ON at point M? We have this angle that is equal to 90 degrees plus the missing angle. In total they must be equal to 180 degrees. So the missing angle must be equal to 90 degrees. So we actually have here OM, line segment OM is perpendicular to chord FD. So I'll write it down. OM, and OM exists from the center of the circle, that is to say from point O, is perpendicular to chord FD. Therefore, according to rule number 2, whenever you draw a perpendicular from the center of a circle to any chord, it will bisect the chord. Therefore, perpendicular OM bisects chord FD according to rule number 2. That is to say, FM equals to MD. FM equals to MD according to rule number 2. Okay. What is actually FM? FM, you can see here that FM is FA plus AM. So we can substitute Fm by Fa plus Am, and it is equal to Md. So here Md, it is actually Me plus Ed. So we can substitute Md by Me plus Ed. So in conclusion, we found out that Fa plus Am equals to Me plus Ed. Okay? But we have already found out that Am equals to Me. Here Am equals to Me, and because of the fact that those two line segments are equal to each other, we can cancel them out from the equation, and we're left only with Fa that is equal to Ed. Here line segment Fa equals to line segment Ed, but we have already found out that line segment Ed equals to 5 units. So Ed equals to 5, and from this equation Fa equals to Ed equals to 5, we will derive that Fa is also equal to 5 units. Here Fa equals to 5 units. In the next step, we will extend side BA by a straight line until it touches the circle. We will define the touching point of the extended side BA and the circle as point P. So here we have chord FD that intersects with chord PB, point A. And according to the old new rule number 2, whenever you have two chords that intersect with each other, you can use a certain formula. Here, chord AB intersects with chord CD at point O. Therefore, according to this old rule number 2, AO times OB equals to CO times OD. Then again, AO times OB equals to CO times OD. So we actually can implement in our drawing rule number 2. Why? Because in our drawing, as I already mentioned before, chord FD intersects with chord PB at point A. I'll write it down. Now, original drawing, we have chord FD that intersects with chord PB, and the intersection point occurs at point A. Therefore, according to the old rule number 2, we will get that Fa times AD equals to PA times AB. Again, Fa times AD equals to PA times AB. Fa times AD equals to PA times AB. Repeat again, according to the old rule number 2, we get that Fa times AD equals to PA times AB. Fa equals to 5 units, AD equals to 18 units, and it is equal to PA. PA is the missing line segment, so we leave it as it is, times AB. AB equals to 6 units, so we will substitute AB by 6. So in conclusion, we found out that according to old rule number 2, 5 times 18 equals to PA times 6. Here we will divide this equation by 6, and we will get that PA, the missing line segment PA, equals to 5 times 18 over 6. So PA equals to 18 over 6 is 3, and 3 times 5 is 15 units. So PA equals to 15 units. Write it down here. Okay. In the next step, I will present to you a new rule, and we will implement the new rule in our drawing. According to the new rule, that will be actually rule number 2, rule number 4 of course. according to rule number 4, whenever you have two chords that are perpendicular to each other, you can use a certain formula in order to find out the radius of the circle that contains the chords. So I will draw the drawing in order to clarify the rule. So we have a circle that could be any circle. The center of the circle will be at point E here. And we have here chord AB. This is chord AB. This is actually perpendicular to chord CD. Chord AB is perpendicular to chord CD. That is to say, the intersection point they create between them 90 degrees. Here, this angle equals to 90 degrees. We will define the intersection point of the two chords with each other as point O. So as you can see here, the two chords A, B and CD are perpendicular to each other. That is to say they create between them at the intersection point 90 degrees. This angle equals 90 degrees. So if chord AB is perpendicular to chord CD, then the following equation will be true. We define the radius of this circle as capital R. Here EM equals to capital R according to our definition. 4 times R squared will be equal to AO squared plus OB squared plus CO squared plus OD squared. Okay, so whenever you have two chords that are perpendicular to each other, you actually can find out the radius of the circle that contains the two chords that are perpendicular to each other by using this formula. Okay, 4 times R squared, R is the radius of this circle, it is equal to AO squared plus OB squared plus CO squared plus OD squared. So we actually can implement rule number 4 in our drawing. Why? Because in our drawing we have chord FD that is perpendicular to chord PB. They create between them 90 degrees at the intersection point, point A. For that reason we can use here rule number 4. So we write it down. In our original drawing we have chord FD is perpendicular to chord PB. So here, chord FD is perpendicular to chord PB. For that reason, you can use rule number 4. And according to rule number 4, we get here, we define the radius of this circle as capital R, or M equals to capital R according to our definition. So the following equation, whenever you have two chords that are perpendicular to each other, the following equation will be true, that 4 times capital R squared equals to FA squared plus AO squared plus PA square plus AB square. Okay, repeat again. 4R square, R is the radius of the circle. It contains the two chords that are perpendicular to each other, equals to FA square plus AO square plus PA square plus AB square. So 4R square equals to FA square. FA equals to 5, so FA square equals to 5 squared, that is 25, plus AO square. AO equals to 18 units, therefore AO square equals to 18 squared, that is 324, plus PA square. PA equals to 15 units, therefore PA square equals to 15 squared, that is 225, plus AB square. AB equals to 6, so AB square is 6 squared, that is 36. So in conclusion, we found out that 4R square, R is the radius of the circle, equals to 25 plus 225 is 250, plus 324 plus 36 is 360. So 4R square equals to 250 plus 360, that is 610. Here we'll divide this equation by 4 and we'll get that R square equals to 610 over 4. Here we'll take a root out of this equation and we'll get that R, the radius that we are looking for of this circle of capital R, equals to the square root of 610 over 4. That is to say, it is equal, the radius of the circle equals to the square root of 610, and the square root of 4 is 2. So the radius of this circle equals to either the square root of 610 over 2 units, or in terms of numbers, it is equal to 12.349 units. So we finished with the second method. In the next step, we'll summarize the lecture and start with the first method, of course. So in the drawing we have a circle, the center of the circle is at this point, point O. Line segment AB equals to 6 units, line segment BC equals to 13 units, line segment AD, this line segment equals to 18 units, this angle BAD equals to 90 degrees, this angle ABC equals to 90 degrees also. Our mission is to find out the radius of this circle. Here we define the radius of this circle OM as capital R, so we have to find out the value of capital R. So first of all, we did the construction from point D. We drew perpendicular on from point E. From point E, we drew perpendicular from point C. Here from point C, we drew perpendicular on AD. That is to say, this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AD is E. By doing this construction, we created quadrilateral ABEC that has 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. And therefore quadrilateral ABEC that has 4 right angles, we relate to it as a rectangle. And we know that the opposite sides of a rectangle are equal to each other, that is to say AB equals to EC. But AB equals to 6, therefore EC must be also equal to 6 units. Likewise, according to the sum rule that the opposite sides of a rectangle are equal to each other, we will get that BC equals to AE. But BC equals to 13 units, therefore AE must be also equal to 13 units. What is the length of ED? From the drawing it is already to see that ED equals to AD minus AE. AD is 18, AE is 13, 18 minus 13 is 5. So ED equals to 5 units. Okay, then we joined points C and D together by a straight line. In this way we created the green small right triangle EDC, and then we implemented the Pythagoras theorem on the green small right triangle EDC. Here by PT is a relation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this green small triangle is DC, therefore the square of the hypotenuse is DC square, and it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to EC square plus ED square. So in conclusion, according to the Pythagoras theorem, DC square equals to EC square plus ED square. EC equals to 6, so EC square equals to 6 square, that is 36. Plus ED square, ED equals to 5, therefore ED square equals to 5 square, that is 25. So in conclusion, we found out that DC square equals to 36 plus 25. 36 plus 25 is 61. So we found out that DC square equals to 61, so we took a root out of this equation and found out that DC, the hypotenuse of the right triangle in DC, equals to the square root of 61. Here, the hypotenuse DC equals to the square root of 61 units. Then we join points B and D together by a straight line. By joining points B and D, we created the right triangle, this right triangle ABD. We implemented the Pythagoras theorem, this right triangle ABD, in order to find out the length of the hypotenuse BD. So we have the right triangle ABD by PT is a relation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is BD, therefore the square of the hypotenuse is BD square, and it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to AB square plus AD square. AB equals to 6, therefore AB square equals to 6 square, that is 36, plus AD square. AD equals to 18 units, therefore AD square equals to 18 square, that is 324. In conclusion, we found out that BD square equals to 36 plus 324, that is 360. So BD square equals to 360, then we substituted 360 by 36 times 10, then we took a root out of this equation and we found out that BD equals to the square root of 36 times 10. Then we took 36 out of the root, the square root of 36 is 6, so in conclusion we found out that the length of the hypotenuse BD equals to 6 times square root of 10 units. Then in the next step, we calculated the area of this green triangle, triangle BDC. The area of any triangle, and especially the area of the green triangle BDC, equals to the base of the triangle times the height to the base over 2. The base must create 90 degrees with the height. So here we choose the base of the green triangle as BC, so we substitute the base by BC times the height over 2. Then in order to find out the height to the base BC of the green triangle, we extended side BC by straight line, and from point D we draw perpendicular on the extended BC. We define the touching point of the perpendicular from point D and the extended BC as F. So this angle equals 90 degrees and this angle equals 90 degrees according to our construction. Okay. By doing this construction, we created the quadrilateral ABDF. This quadrilateral has 1, 2, 3 right angles, therefore this fourth angle must be also equal to 90 degrees, and therefore quadrilateral ABDF that has 4 right angles, we will relate to it as a rectangle. Here, quadrilateral ABDF is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other, that is to say AB equals to DF. Here AB equals to DF, but according to what is given as the question, AB equals to 6, therefore here AB equals to 6, and from this equation 6 equals to AB equals to DF, we will derive that DF it is also equals to 6 units. Here DF equals to 6 units, but DF it is the height because it creates 90 degrees with the extended BC. Therefore, we actually found out that the height to the base BC it is equal to 6 units. Now we can easily find out the area of this green triangle BDC. The area of the green triangle BDC equals to the base that is BC, but BC equals to 13, so we substitute BC by 13 times the height. The height is 6 units. That is what we have just found out. So the height is 6 over 2. 6 over 2 is 3, and 3 times 13 is 39. In conclusion, we found out that the area of this green triangle BDC equals to 39 square units. Then I presented to you a new rule, and we implemented the new rule in our drawing. According to the new rule, if this triangle ABC, that could be any triangle, is blocked by a circle, by this circle, that could be also any circle, then the following equation will be true. Here, this is triangle ABC. Side AB equals to a unit in its length, side AC equals to 0 units in its length, and side BC equals to 3 units in its length. And here, the radius of this circle OM equals to capital R according to our definition. So we can find out the radius of the circle that blocks a triangle only by knowing the side lengths of the triangle that is blocked by the circle, and also the area of the triangle that is blocked by the circle. And the radius of this circle, that is to say capital R, will be equal to A times B times C, that is the side lengths of the triangle that multiplied by each other, over 4 times the area of triangle ABC that is blocked by the circle. So we can actually implement rule number 1 in our drawing. Why? Because in our drawing we have the green triangle BDC that is blocked by this circle. But in order that the triangle will be blocked by a circle, or the 3 vertices must touch the circle. This vertex of triangle BDC touches the circle at point B. This vertex of triangle BDC touches the circle at point C, and finally this vertex touches the circle at point D. Therefore, we can implement rule number 1. So I repeat again. Triangle BDC is blocked by the circle, and therefore, according to rule number 1, the radius of this circle that blocks triangle BDC, we define the radius of this circle as capital R. Capital R will be equal to the multiplication of the side lengths of the green triangle by each other. That is to say, it is BD times BF, BD times BC times DC. Again, it is BD times DC times BC over 4 times the area of the green triangle BDC. Over 4 times the area of triangle BDC. BD equals to 6 times square root of 10 units. DC equals to the square root of 61 units, and BC equals to 13 units. Over 4 times the area of triangle BDC. We already found out that the area of triangle BDC equals to 39 square units. So that is actually the answer to our question. We asked to find out the radius of this circle, and the radius of this circle equals to this expression. Capital R equals to this expression. We will just simplify this expression, and then we'll move to the second method. So here we divided both the numerator and the denominator of this expression by 13. So here 13 over 13 is 1, so 13 will get cancelled, and in the numerator we left only with 6 times square root of 10 times square root of 61. We have to divide the denominator by 13. So we have 4 times 39. 39 over 13 is 3. So in total, in the denominator we left only with 4 times 3, that is 12. So in conclusion, the radius of the circle equals to 6 times square root of 10 times square root of 61 over 12. Here we divided both the numerator and the denominator of this expression by 6. 6 over 6 is 1, so 6 will get cancelled. And we left only with square root of 10 times square root of 61 over 12 over 6 is 2. So the radius of the circle equals to the square root of 10 times square root of 61 over 2. According to the algebraic identity, the square root of a times square root of b equals to the square root of a times b. We get that the square root of 10 times square root of 61 equals to the square root of 10 times 61, all divided by 2. 10 times 61 is 610. In conclusion, we found out that the radius of this circle, capital R, equals to either the square root of 610 over 2 units, or in terms of numbers, it is equal to 12.349 units. So we finished with the first method. Then I presented to you the second method to find out the radius of this circle. In the second method, in the first step, we did all the things that we already done in the first method. So I repeat on it quickly. That is to say, from point C we draw perpendicular on AD. This angle equals 90 degrees, this angle equals 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AD as E. So inside quadrilateral ABEC that we created by our construction, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. Therefore, inside quadrilateral ABC, we have 4 right angles. Therefore, quadrilateral ABC is it is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. That is to say, AB equals to EC, but AB equals to 6. Therefore, EC must be also equal to 6. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we will get that BC equals to AE. But BC equals to 13 units, therefore AE must be also equal to 13 units. What is the length of ED? ED equals to AD minus AE. That is to say, it is 18 minus 13, that is 5. So until now we did all the things that I mentioned here in the first step. From now on, we will move to the second method. In the second method, from point O, that is the center of the circle, we draw perpendicular on chord BC. So this angle equals 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and chord BC as capital N, and we define the touching point of the perpendicular from point O and AD as capital M. Then I presented to you rule number 1, and we implemented rule number 1 in our drawing. According to rule number 1, whenever you have from the center of the circle perpendicular to any chord, it will bisect the chord. Here, a perpendicular from the perpendicular from the center of a circle to any chord, bisect the chord. So here we have from the center of the circle, that is to say from point O perpendicular OM to chord BC. Why it is perpendicular? Because this angle equals to 90 degrees and this angle equals to 90 degrees. So the perpendicular OM bisect chord BC. It means that BM equals to MC. Okay, so we can actually implement rule number 2 in our drawing. Why? Because in our drawing we have perpendicular ON to chord BC. Perpendicular OM exists from the center of the circle, that is to say from point O on chord BC. And according to rule number 2, it bisects chord BC. That is to say BN equals to NC. So I repeat again. In our original drawing, we have perpendicular ON from the center of the circle. That is to say from point O it bisects to chord BC, and according to rule number 2, it bisects chord BC. That is to say, BN equals to NC, according to rule number 2. Okay, then we focused on quadrilateral ABMN. In this quadrilateral, we have 1, 2, 3 right angles. Therefore, this fourth angle must be also equal to 90 degrees. And therefore, quadrilateral ABMN is a rectangle. You can see quadrilateral ABMN is a rectangle because it has 4 right angles, and we know that the opposite sides of a rectangle are equal to each other. That is to say, AM equals to BN. AM equals to BN. Likewise, we focus on quadrilateral MNEC. In quadrilateral MNEC, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. Therefore, quadrilateral MNEC that has 4 right angles, it is a rectangle. And we know that the opposite sides of rectangle are equal to each other. Here, quadrilateral MNEC is a rectangle because it has 4 right angles. The opposite sides of rectangle are equal to each other. That is to say, ME equals to NC. ME equals to NC. So what we did, we can summarize what we did until now. According to rule number 2, we found out that BN equals to NC. And according to the rule that the opposite sides of a rectangle are equal to each other, we found out that BN equals to AM. Here, BN equals to AM. And according to the sum rule, we found out that NC equals to ME. So we can write here that NC equals to NC equals to ME. NC equals to ME. And from this long equation, MA equals to BN equals to NC equals to ME, we will derive that AM equals to ME. Here, side AM equals to side ME. In the next step, we extended line segment AD or line segment DA until it touches the circle at point F. Okay, in this way we created chord FD. By doing this construction, we created chord FD. Here, a couple minutes ago, we drew perpendicular ON on chord BC. ON as a perpendicular, it is absolutely a straight line. So if we focus on the upper side of ON at point M, the sum of the angles must be equal to 180 degrees according to rule number 1. So which angles we have at the upper side of ON at point M? We have this angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees according to rule number 1. So this missing angle must be equal to 90 degrees. Likewise, we focus on the lower side of the straight line ON at point M. Here, the sum of the angles must be equal to 180 degrees according to rule number 1. So which angles we have at the upper side of OM at point M? We have this angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees. Therefore, the missing angle here must be equal to 90 degrees. So I actually found out that OM is perpendicular to chord FD. Why? Because this angle equals to 90 degrees, this angle equals to 90 degrees, therefore line segment OM is perpendicular to chord FD, and line segment OM exists from point O, that is the center of the circle. Here, perpendicular here actually found out that line segment OM is perpendicular to chord FD. Therefore, whenever from the center of the circle you have perpendicular to any chord, it bisects the chord. That is to say, perpendicular OM bisects chord FD. That is to say, FM equals to MD, according to rule number 2. According to rule number 2, FM equals to MD. But what is FM? FM is FA plus AM. So we can substitute FM by FA plus AM, and it is equal to MD. What is actually MD? You can see it here that MD equals to ME plus ED. Okay, MD equals to ME plus ED. So we can substitute MD by ME plus ED. In conclusion, we found out that FA plus AM equals to ME plus ED. But we already found out that AM equals to MF. Here AM equals to, here it is actually E. This letter is E. Extended it, called it F, but it is E. AM equals to ME. That is to say, AM called line segment AM equals to line segment ME. Therefore, we can cancel them out because they are equal to each other. And we left only with FA that is equal to DE. Here code FA equals to code ED. Okay, FA equals to ED. But we have already found out that ED equals to 5 units. So we can write here that ED equals to 5 units, and from this equation FA equals to ED equals to 5, we will derive that FA it is also equals to 5 units. Here FA equals to 5 units. In the next step, we extend that. In the next step, we extended side BA by straight line until it touches the circle at point P. And then we have here code FD that intersects with code PB at point A. Therefore, we can implement here the old rule number 2. I remind you what is old rule number 2. According to the old rule number 2, if code AB intersects with code CD at point O, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. Okay, so according to the old rule number 2, we will get that FA times AD equals to PA times AB. Again, FA times AD equals to PA times AB. Because code FD intersects with code PB at point A. So repeat again. Code FD intersects with code PB at point A. Therefore, according to the old rule number 2, FA times AD equals to PA times AB. Repeat again. FA times AD equals to PA times AB. FA equals to 5 units, AD equals to 18 units, PA is the missing line segment, so we will leave it as it is, AB equals to 6 units. So we will substitute AB by 6. In conclusion, we found out that according to the old rule number 2, 5 times 18 equals to PA times 6. We divided this equation by 6, and we found out that PA equals to 5 times 18 over 6. 18 over 6 is 3, and 3 times 5 is 15. So we found out that this line segment PA equals to 15 units in its length. Now I presented to you a new rule, and we implemented the new rule in our drawing. According to the new rule, this is actually rule number 4. Whenever we have two chords that are perpendicular to each other, then we can find out the radius of this circle according to this formula. Here we have chord AB that intersects with chord CD at 90 degrees. That is to say they are perpendicular to each other at this point O, the intersection point. So if the radius of this circle EM equals to capital R, then we can find the radius of this circle by this formula that states that 4R squared, R again is the radius of this circle, it will be equal to AO squared plus OB squared plus CO squared plus OD squared. Again, 4R squared, R is the radius of this circle, equals to AO squared plus OB squared plus CO squared plus OD squared. Actually, we can implement this rule number 4 in our drawing. Why? Because in our drawing, we also have two chords that are perpendicular to each other. That is to say, chord FD, this chord, is perpendicular to chord PB. Why they are perpendicular to each other? Because they create between them at the intersection point 90 degrees. Therefore, they are perpendicular to each other. Therefore, we can implement here rule number 4. I'll repeat again. In our drawing, we have chord FD that is perpendicular to chord PB at point A. Therefore, we can implement here rule number 4. According to rule number 4, if the radius of this circle is equal to capital R, that is to say OM equals to capital R, then we can find out the radius of this circle according to the following formula, that 4 times r squared, again r is the radius of this circle, equals to fa squared plus ad squared plus plus pa squared plus ab squared. Again, 4 times r squared equals to fa squared plus ad squared plus pa squared plus ab squared. I repeat again. 4r squared equals to fa squared plus ad squared plus pa squared plus ab squared. So 4r squared equals to fa squared. Fa equals to 5, therefore fa squared equals to 5 squared, that is 25, plus ad squared. Ad equals to 18 units, so ad squared equals to 18 squared, that is 324, plus pa squared. Pa equals to 15 units, therefore pa squared equals to 15 squared, that is 225, plus ab squared. AB equals to 6 units, therefore AB squared is 6 squared, that is 36. So in conclusion, we found out that 4r squared equals to 25 plus 225 is 250, and 324 plus 36 is 360. So 4r squared equals to 250 plus 360, that is 610. So 4r squared equals to 610. We divided this equation by 4, and we found out that r squared equals to 610 over 4. Here we took a root out of this equation and found out that r, the radius, that is to say the radius of this circle, the radius that we are looking for, equals to the square root of 610 over 4. That is to say r equals to the square root of 610 over the square root of 4 is 2. So the answer to this question is that the radius of this circle, that is to say OM, that is capital R, is equal to either the square root of 610 over 2 units, or in terms of numbers, it is equal to 12.349 units. Okay, thank you very much.